Hello, this is the section 3.6 lesson on the topic of joint distributions. This is going to be a very condensed version of this section. We're going to focus on just the most important ideas in this section. So let's start off with an example from section 3.3. Let's suppose a random variable x is uniformly distributed over the interval 0 to 1. So remember what uniformly distributed means. It means that everything is equally likely. So x takes values between 0 and 1, and everything is equally likely. Now, once we've identified the distribution of this random variable, we could describe its PDF. And so according to our meaning of the uniform distribution, the PDF of this is going to be 1 divided by the largest value minus the smallest value, which is going to be 1. So we've got a constant PDF equal to 1. So now let's suppose we wanted to find a probability of this random variable. Find the probability that x is between 0.25 and 0.8. Well, by our definition of the PDF, we would find this by integrating the PDF from the smallest value, 0.25, to the largest value of 0.8. And we could very easily do this because we have a constant integrand. So to evaluate this, we take our constant integrand times the width of our interval, 0.8 minus 0.25. We do that arithmetic, and we're all done. So the main point of this example is to illustrate that to find a probability, we integrated the PDF over the interval of interest. In this case, our interval was from 0.25 to 0.8. So we integrated our PDF over that interval, and we're all done. Now, some random experiments involve more than one random variable. So as an example, let's suppose we randomly select a point from this rectangle down here. So this rectangle here is drawn on the xy plane. So the x values here go from 0 to 1. The y values go from 0 to 2. Notice that our rectangle here isn't to scale, but that's not a big deal. And so we select a point inside this interval. So suppose we select this point right here. Well, that point has an x-coordinate and a y-coordinate. Well, both of those coordinates are numbers associated with an outcome of this random experiment. And so both of those are random variables. So let's define those random variables. Let's let x equal the x-coordinate of the point, and then y equals the y-coordinate of the point. So we have one random experiment and two different random variables. Okay. Well, now let's make a couple of observations about these random variables. First of all, x only takes values between 0 and 1. Likewise, y only takes values between 0 and 2. And we're randomly selecting a point. So that means it's just as likely that x is, say, over here close to 0 as it is close to 1 as it is in the middle. Likewise, we're randomly selecting a point, so the y-coordinate is just as likely to be down here as it is to be up here as it is to be in the middle. And so that indicates that both x and y are uniformly distributed. So x is uniform over the interval 0 to 1, and y is also uniform over the interval 0 to 2 in this case. So we know the distributions of these two random variables, so we can describe their PDFs. So the PDF of x is 1 over 1 minus 0. The PDF of y is 1 over 2 minus 0. So the PDF of x we're going to denote f sub x. The PDF of y will denote f sub y. We give them these subscripts so that we can distinguish one PDF from the other. We don't want to just call them a generic f because we've got two random variables involved. We want to keep these PDFs distinguished from each other. Now, in the context of a situation where we have two random variables, these PDFs are called the marginal PDFs. Now, don't let that word marginal scare you. It's just a name that we use in a context where we have more than one random variable. So this marginal PDF of x is just a regular PDF that we could use to calculate probabilities. Likewise, this marginal PDF of y is a PDF, just like we've seen before, that we can use to calculate probabilities of y. Okay. Well, now let's ask a question about this random experiment. We might ask, what is the probability that the x-coordinate of the point is less than the y-coordinate of the point? Now, why are we interested in that? Well, I don't know, but let's just use this as an example. Okay. So what we have here is a probability about some sort of combination of our two random variables. So let's think about this graphically. We've got our rectangle here, and I'm going to draw the line y equals x here. And so for points above that line, y is greater than x, so that means the y-coordinate is greater than the x-coordinate. And for points below that, the y-coordinate is less than the x-coordinate. So graphically speaking, our question can be stated as this. What's the probability that the point is in this region up here, for which the x-coordinate is less than the y-coordinate, or equivalently the y-coordinate is greater than the x-coordinate? So we want to ask, what's the probability that our point is here inside of this region? So in mathematical terms, using our random variables x and y, we want to ask, what's the probability that a random variable x is less than the random variable y? So here we've got a probability involving both these random variables x and y. So we want to calculate this probability that x is less than y, which is again a probability involving both of our random variables x and y. And so to calculate this, kind of using the same terminology as in our first example, we're going to need to integrate something. So informally, we're going to need to integrate something that combines the marginal PDFs of x and y over the region of interest. Okay? Just like in that first example, we integrated our PDF of x over the interval of interest. So here we've got something involving a combination of x and y, so we're going to need to integrate something that combines our two PDFs over our region of interest. Now we're not talking about a one-dimensional interval of interest, we're talking about a two-dimensional region of interest. Okay? So in graphical terms, we're going to need to find this something and integrate it over this two-dimensional region of interest up here. Okay? Now that something that we're going to integrate is called the joint PDF of x and y. Called joint PDF because it's a PDF in the sense that we're going to integrate it. Joint because it's a combination of x and y. And this joint PDF is denoted f of x comma y. A little f because it's a PDF, x comma y because it combines x and y. So the next question is, well, how do we find this joint PDF? Well, in order to find this, we're going to review a definition back from section 1.7, where we said two events, A and B, are said to be independent if the probability of A intersect B equals P of A times P of B. So informally, independence means that the occurrence of one event does not affect the probability of the other event occurring. So what we're going to do now is to kind of extend this idea of independence to random variables. So that leads to this definition, 363, which says that two random variables, x and y, are said to be independent if their joint PDF equals the marginal PDF of x times the marginal PDF of y. So in other words, they're independent if their joint PDF is the product of their marginal PDFs. Now informally, this idea of independence means that x and y are independent if the value of one does not affect the value of the other. So kind of the same idea as independence with events, except that we're talking about independence of random variables. the random variables are independent if the value of one does not affect the value of the other. Okay. So let's try to apply this idea back to our example, where we randomly select a point from inside of this rectangle. X is the x-coordinate, y is the y-coordinate. Now, we do this randomly, so that means that our x-coordinate really has no effect on our y-coordinate. And so, in other words, it seems reasonable to assume that x and y are independent. The value of one variable has no effect on the value of the other variable. And so they're independent. So, what does that do for us? Well, remember our marginal PDFs are this. F sub x is 1, f sub y is 1/2. And so because these random variables are independent, their joint PDF is just the product of their marginal PDFs. So we're going to take 1 times 1/2, and that equals 1/2. So here, f of x comma y is equal to 1/2. There's our joint PDF. So there we came up with a very, very simple formula for our joint PDF. So let's go back and use our joint PDF to try to calculate our probability. So we want to calculate the probability that x is less than y. And so we're going to integrate our joint PDF over our region of interest. So here's our region of interest, this quadrilateral shape region. And so we're going to have to integrate over this two-dimensional region. Well, in order to integrate over a two-dimensional region, we need to use a double integral from Calculus 3. And so, in mathematical terms, the probability that we want is going to equal the double integral of our joint PDF. And so we set this up by drawing two integral symbols. We have a dy and a dx. Differentials. So then we start on the outside, and we say over our region of interest, which is this region down here, what are the smallest and largest values of x? Well, obviously here x goes from 0 up to 1, and so we're going to put those as the limits of integration on the outside. Now for the inside limits of integration, we're going to choose a value of x, go up till we hit our region, and keep going till we leave the region. And we ask ourselves, what's that smallest value of y in terms of x? And then what's the largest value of y in terms of x? Well, obviously the smallest value of y is going to be just x, and the largest value of y is going to be 2. So that becomes our limits of integration on the inside, x up to 2. So now to evaluate this double integral, we work from the inside out. So on the inside, we're integrating with respect to y. That means x is a constant. And so our integrand here is just a constant. So we can pull that integrand out front, really. Or state another way, we could take our constant integrand times the width of our interval. So here's our constant integrand. The width of our interval is 2 minus x. And so now we've got here just a regular calculus 1 integral. And so we can pull that 1/2 out front. We integrate the 2, we integrate the x, and then we plug in our limits of integration. And we'll skip all the details there, but there's our end result, 3/4. Okay. So that's all there is to calculating this probability. We integrated our joint PDF over our region of interest, and we're all done. Now let's look at another example. Suppose a man and woman agree to meet at a restaurant sometime between 6 and 6:15 p.m. Find the probability that the man has to wait longer than 5 minutes for the woman to arrive. So notice that we've got here one random experiment. This man and woman are meeting at this restaurant. But we've got really two random variables involved. We've got the time that the man arrives and the time that the woman arrives. So let's define our two random variables here. Let's let x equal the number of minutes past 6 p.m. the man arrives, and y is the number of minutes past 6 that the woman arrives. So both x and y are going to take values between 0 and 15 because they both arrive between 6 o'clock and 6:15. And so in terms of these random variables, the question is, find the probability that y, the time the woman arrives, is more than 5 minutes greater than x, the time that the man arrives. And so in mathematical notation, we want to find the probability that y is greater than x plus 5. And this is just a mathematical way of saying the probability that the time the woman arrives is greater than 5 minutes more than the time that the man arrives. And so in mathematical notation, this is what we want to find. Now, this problem doesn't give us a whole lot of information about these two random variables x and y, so we're going to make two assumptions here. First of all, we're going to assume that both x and y are uniformly distributed over the interval 0 to 15. Now, we already know that both x and y take values between 0 and 15, so we're going to assume that all those values are equally likely. So in other words, we're assuming that it's just as likely that both the man and the woman arrive close to 6 as close to 6:15 as close to 6:10. So that seems like a fairly reasonable assumption. So that means that our marginal PDFs are both 1 over 15 minus 0, so 1 over 15. So there we have our marginal PDFs. Now we're going to make a second assumption that both x and y are independent. So we're going to assume that the time that the man arrives has no effect on the time that the woman arrives. So that means that their joint PDF is the product of their marginal PDFs. 115 times 115 is 115 squared. So there we go. We've got our joint PDF, and so now we can calculate our probability. So in mathematical notation, we want to find the probability that y is greater than x plus 5. So in order to do that, we're going to integrate our joint PDF over our region of interest. So let's look graphically at what our region of interest is. So here's kind of a similar looking rectangle to what we had before. Here x goes between 0 and 15, y is between 0 and 15. And so both our values of x and y are going to be somewhere inside of this big rectangle. And now I drew the line here, y equals x plus 5. Above that line, y is greater than x plus 5. And below that line, y is less than x plus 5. We're interested in y being greater than x plus 5. And so this right here is our two-dimensional region of interest. So we need to integrate our PDF, joint PDF, over that region of interest. So I've got x on the outside. So I ask myself, inside of this region of interest, what is the smallest and the largest value of x? Well, we can see that x can go from 0 up to 10. That right there is the x value of that coordinate. So we're going to put those limits 0 to 10. Next, we ask for a fixed value of x. We go up till we hit the region, keep going till we leave the region. We ask what's that smallest value of y in terms of x, and what's the largest value of y. Well, the smallest value is going to be on this line, so x plus 5. The largest value is going to be 15. So there's our limits of integration for y, x plus 5 up to 15. So now we need to evaluate this double integral. And so we'll skip a lot of the details here, but we start from the inside, integrate with respect to y. So we've got a constant integrand. I'm going to pull that constant integrand out front, and then we're going to multiply that by the width of our interval. So the width of our interval here is 15 minus x plus 5. And so now we need to integrate that with respect to x. We could clean this up here. This is really 10 minus x, so integrate that to get 10x minus x squared over 5. X squared over 2. And then we plug in our limits of x, 0 to 10. We do that arithmetic, and we're all done. 2/9. So that's all there is to calculating this probability.